All right, we spent several days on the tangent ratio, looking at that wherever our reference angle is and doing the leg opposite divided by the leg adjacent. We learned a little calculator work with tangent. Now we're kind of going back to the beginning where we started with tangent, and now we're going to look at the other two ratios, sine and cosine. Now we are looking at them together because they both involve the hypotenuse. One involves the hypotenuse and the leg opposite, and one involves the hypotenuse and the leg adjacent. So that's why we're going to be looking at these two today. So the sine ratio, S-I-N-E, and it is abbreviated S-I-N, but I don't want to hear anyone saying the sin of angle A. Even though the E's not there when we abbreviate it, we still pronounce it sine. So sine is the leg opposite divided by the hypotenuse. The cosine ratio, which is abbreviated COS, is the leg adjacent divided by the hypotenuse. Now remember that opposite and adjacent all depend on where is my reference angle. So that's going to be the most important, is again knowing where my reference angle is, because these are both going to involve the hypotenuse, but it's knowing that I use the correct one at the correct time. If I'm doing sine, I need to make sure I'm using that side opposite the reference angle. And if I'm doing cosine, I need to use that leg adjacent to the reference angle. Now, like we did when we started tangent, we are going to go back and create this table. So you are going to need one computer per group. I don't care who in your group gets their computer out. One computer per group. I put in Google Classroom the activity sine and cosine ratios, and it has a link back to, we're going to use this triangle again. So I'm going to pause here and give you a minute to get that computer out and get to this triangle. All right, so manipulating this triangle is going to be the same as we did for tangent. We're still going by those degree measures. If you look at the chart, though, I'm going to go back to the note page for a minute. The chart, as I scroll down, we have sine at the top of the table, and it does go on to the next page. And then you notice we have cosine. Now, the good news is you can use the same triangle for the sine of 10 degrees and the cosine of 10 degrees because they use different measures, and I'll show you how we're going to do that so that you can really work on filling out both sine and cosine at the same time. You don't have to do just sine and then go back and do just cosine. So again, remember, we're not going to touch angle C. We're going to leave angle C alone. We're only going to manipulate angles A and B. So I'm going to bring B down until I get that reference angle, angle A, down to 10 degrees. Sometimes it's a little tricky. And remember, if you want, you can also manipulate A and bring it in a little. So I'm going to use this triangle right here for my triangle. Yours can be different. It doesn't have to have the same numbers, but when it comes to the division, if you're not using mine, then you do need to do your own math on this first one. So I'm going to draw my triangle on my notes where it says sketch. So I'm going to sketch triangle A, B, C. C is my right angle. Now I've already forgotten my measure, so let me go back and look. 11.1 for my hypotenuse. 10.9 and 1.9 for my legs. And again, angle A is 10 degrees. And that's going to be my reference angle. Reference angle still comes to play here with our sine and cosine, just like it did with tangent. And again, we're not using the sine or cosine keys today. This is just division in your calculator. So remember the sine ratio, the sine of angle A, I'm going to write it at the top just so we remember, is opposite over hypotenuse. And I am abbreviating both of those. So I need the side opposite the 10 degrees divided by the hypotenuse. So which of my measures here on my triangle is going to represent the side opposite the reference angle? which measure is opposite of my reference angle of 10 degrees? Which measure is opposite? The 1.9 would be my opposite. It's across from that 10 degrees, so that would be opposite the reference angle. Hypotenuse is always opposite the right angle, so the 11.1, and it has to be the longest side. So as a ratio, the sine of 10 degrees is 1.9 divided by 11.1. Now, the next column, they just want me to take that 1.9 divided by 11.1 and turn it into a decimal, rounded to 3 places. So the sine of 10 degrees is 0.171. Now again, I can use that exact same triangle for cosine. So I'm going to scroll down to cosine, redraw that exact same triangle down in cosine of 10 degrees. What was my other? Was it 10.9? Because now cosine, the cosine of angle A is adjacent over hypotenuse. Now, the hypotenuse has not changed. The 11.1 is still repping my hypotenuse. If the 1.9 was my opposite, then the 10.9 has to be my adjacent. So this is how I can use the same triangle because it's looking at 2 different ratios. So the cosine of 10 degrees is 10.9 divided by 11.1. And when I turn that into a decimal, 10.9 divided by 11.1, I get 0.981. So I used the same triangle for both sine and cosine, so I'm working both charts at the same time. So I only have to draw, you only have 7 more triangles instead of having to do 14. I would not waste the time of doing sine and then having to go back and get those angle measures back and do cosine. Once you get the 10, the 20, the 30, do both of your sine and your cosine at the same time using the same triangle. That will help move this along. So I'm going to pause while you and your table complete both the sine and cosine chart. All right, so we should have our sine and cosine table completed. Yesterday we started on this table, making sure that to cut down the time in making the table, I showed you how you could use the same triangle for the sine of 10 and the cosine of 10 because they were doing opposite measures, so that you could, one you could use an opposite over hypotenuse, the other one adjacent over hypotenuse to get those values. Now again, I am not filling out the entire chart because everyone's pictures are probably different. Everyone's ratios could be different, but we should all have very close decimal values no matter what ratios we're using. So I am going to go through the groups and have you share your different values. So I did sine and cosine of 10 with you, so we should all have the exact same thing there. But let's now move on to the sine of 20 degrees. So starting right here in front of me, what did we get for the decimal for the sine of 20 degrees? Oh, sorry, okay. What was that, Sergio? 0.345. Oops, 345. So working back towards me, the sine of 30 degrees, no, it'd be Alex and Layla. What was our decimal for the sine of 30 degrees? Okay, 0.58. And since they wanted 3 places, then we would say 0. All right, so Mr. Mendoza, do you have the sine of 40 degrees? 0.642. That is a 0 out in front. All right, then Gabriel, your group, the sine of 50 degrees. 0.866. Was that sine of 50 or sine of 60? And say 768. And I'm going to help everybody out because I'll use your sine because I think that was 60 degrees that you gave me there. The 866, right? Okay. Thank you for giving me 2 of them. Jocelyn, what do we have for the sine of 70 degrees? What's your triangle? What are your measures for 70 degrees? All right, next group over, sine of 70 degrees. We can't have a 1. None of our answers can start 1 point. If we have 1 point, that means we did not set up our division correctly. So for the sine of 70 degrees, what did you have for the measure of the leg opposite of the 70 degrees? So if we go back to, you gave me the opposite was 41 point. Leah, what did you say the opposite was? 41.1 divided by, your hypotenuse was 43.7. Based on those measurements, you should have gotten 0.941. But again, making sure, this is very, very important. We know this is why sine and cosine were also saved for after tangent, because they both involve the hypotenuse. We have to remember the hypotenuse has to be the longest leg of a right triangle, which means we can't get an answer bigger than 1, which is how I knew the answer was wrong immediately, because the denominator is always going to be larger than the numerator, giving you an answer less than 1. But that's something we have to think internally. I can't have a hypotenuse that is greater than a leg. All right, Destiny, what'd you guys get for the sine of 80 degrees? 0.985. All right, Victor, what did you get for cosine of 20 degrees? 0.943. All right. Julian, what did you get for the cosine of 30 degrees? Repeat that for me. Cannot be 0.153. What was your opposite leg for your, your adjacent leg, because we're in cosine? 50, and what was your hypotenuse? 15. Well, Okay, so 15 divided by 17.3, we should have been about 0.868 or 867 when I divide those two numbers you just gave me. So this one thing this tells us, we need to be careful when we're setting up our division. We need to make sure we're using the correct values. All right, so Sergio, back to your group. What did you guys get for the cosine of 40 degrees? 0.768. And Alex and Layla, the cosine of 50 degrees? 0.644. All right, Mr. Mendoza, the cosine of 60 degrees? 0.500. All right, Ariana, the cosine of 70 degrees? 0.344. And Matthew, what did you guys get for the cosine of 80? 0.174. So again, you notice none of these answers are greater than 1. Every single one of these answers is between 0 and 1. And again, that comes back to the fact that the hypotenuse is the longest side of a right triangle, and it's the divisor in each case. So you're dividing a smaller number by a bigger number, which means you have to have an answer between 0 and 1. Now, like we did with the tangent ratio, let's go back and see what the actual calculator values are to show you how close you guys are with your ratios. Now again, there's room for human error because that triangle you used was drawn by a human, so there could be a little bit off there. And even though it said like 10 degrees on your screen, it could have been a little bit more or a little bit less than 10 degrees, throwing off the measurements just slightly. So the calculator value for the sine of 10 degrees is 0.174. The sine of 20 degrees, 0.342. The sine of 30 degrees, 0.500. The sine of 40 degrees, 0.643. The sine of 50 degrees, the actual value is 0.766. The sine of 60 is 0.866. The sine of 70, 0.940. And the sine of 80 degrees, 0.985. So some of those were spot on. Some of them were very, very close. Some groups may have had more that were spot on than others, again, depending on what your triangles look like, since we all used different triangles. So the cosine of 10, the calculator value is actually 0.985. The cosine of 20, 0.940. The cosine of 30, 0.866. The cosine of 40, 0.766. The cosine of 50, 0.643. The cosine of 60, 0.500. The cosine of 70, 0.342. And the cosine of 80, 0.174. So again, those are the actual calculator values versus your ratios, which again are all very, very close to the actual values. But now we're going to go back and we're going to look at these charts and we're going to do a little bit of analyzing of what's happening here with these different charts. So the first question in task B says, based on the table, what happens to the sine ratio as the reference angle increases? So going back to just the sine ratios, what is happening to the ratio as the reference angle increases? I'll give you a moment to look back at your chart. All right, so based on the table, what happens to the sine ratio as the angle measure increases? What happened to that ratio as the angle measure got larger? I mean, we started out sine of 10 was at 0.174 and the sine of 80 was 0.985. So as the angle measure increased, what happened to the sine ratio? It increased. So as the angle measure increased, so the sine ratio is increasing as the measure of the reference angle increases. Which means the hypotenuse and opposite leg get closer to being the same length. The hypotenuse and opposite leg get closer to being the same length. Number 2, based on the table, what happens to the cosine ratio as the reference angle measure increases? So again, we started out at cosine 10, we ended at cosine 80. What happened to that ratio as our angle got bigger? The ratio was decreasing. It was working the opposite. Sine, the angle increased, the ratio increased. Cosine, the angle increased, the ratio was decreasing. So the cosine ratio is decreasing as the measure of the reference angle increases. which means the hypotenuse and adjacent leg are getting farther apart in measure. Number 3, if A is an acute angle, then why do sine A and cosine A always have to be between 0 and 1? And I actually already addressed this. When someone gave me an answer that was 1 point something, I knew that there was something wrong. Why did I say I knew there was something wrong? The hypotenuse is always going to be the longest leg, and we are dividing by the hypotenuse for both sine and cosine. And when you're dividing by a bigger number than your numerator, your answer is always going to have to be a number less than 1. And since these are measures, it does have to stay positive, so it would stay between 0 and 1. So both sine and cosine divide by the hypotenuse. Which is always the longest side of a right triangle. The numerator will always be smaller than the denominator. Question 4 says, compare both tables. Did you make any interesting observations? So I'm going to pause for a moment while you and your group go back and look at the two tables. And besides the observations we've already answered in 1, 2, and 3, we already know sine is increasing with the angle measure, cosine is decreasing with the angle measure, and we know that the answer will always be between 0 and 1. Besides those 3 observations, as a group, talk about anything else you notice between the two charts. I'll give you about 2 minutes to talk that over. So again, they're asking about what observations did you make. So if I go back, I'm going to kind of go to this part of the table so we can see a little bit of sine and a little bit of cosine at the same time. What observations did we make about the two tables? Again, besides what we already answered in questions 1, 2, and 3. Any other interesting observations that you came up with? Yes, sir. So sine 80 degrees is equal to cosine 10 degrees. What about sine of 70 and cosine of 20? Does that exist there as well? Did they both come out to 0.940? What about sine of 60 and cosine of 30? Does that exist there too? Yeah, so if you look throughout the table, the sine of 10 degrees is equal to the cosine of 80 degrees, which equaled 0.174. The sine of 20 degrees equaled the cosine of 70 degrees, which equaled 0.342. The sine of 30 degrees equaled the cosine of 60 degrees, which equaled 0.500. The sine of 40 degrees equals the cosine of 50 degrees, which equaled 0.643. The sine of 50 degrees equals the cosine of 40 degrees, equals 0.766. The sine of 60 degrees equaled the cosine of 30 degrees, equaled 0.866. The sine of 70 degrees equaled the cosine of 20 degrees, equals 0.940. And the sine of 80 degrees equaled the cosine of 10 degrees, equaled 0.985. So what do you notice about all of those combinations? Well, the ratios are equal, but what else? I gave you that information. But what do you notice about the combination of the angles? I'll pause and give you a moment to think about that. So again, we know that the combination there equals the same ratio. But what I'm trying to get you to see is, what do you notice about the combinations that got that same ratio? Again, sine of 10 and equals cosine of 80. Sine of 20 equals cosine of 70. Sine of 30 equals the cosine of 60. And that pattern keeps going. What do you notice about that pattern? Again, we know they have the same ratio. We're showing that. But what else do you notice about that pattern? They what? Right, so they are going backwards from each other. Sine is going from 10 to 80. Cosine is going from 80 to 10. So that is, they are going in opposite directions of each other to make that equal happen. So what else, though, about those specific angle measures do you notice in these combinations? Because that is absolutely correct. We're going, and that goes actually showing the answers of questions 1 and 2, how that works. Question 1, we were increasing while our angle increased. And question 2, we were decreasing while our angle increased. So yes, they are moving in opposite directions, which is a great observation. But looking now, I'm trying to get you to look specifically at the angle measures. What do you notice about each of those combination of angle measures in each of those equations? I've got 10 and 80, 20 and 70, 30 and 60, 40 and 50, 50 and 40. 60 and 30, 70 and 20, 80 and 10. Anything. What is 10 plus 80? 90. What is 20 plus 70? What is 30 plus 60? Each of these combinations has to add up to 90 degrees. And we're going to talk about why in a few minutes. We're going to get back to that. But that's what I want you to see. Yes, they're working in opposite directions of each other. So when one's at the low end of its spectrum, the other one's at the high end to get that same ratio. So yes, they work opposite of each other, but we also have to keep in mind that 90, okay? Those numbers, the actual angle measures, taking out the sine and cosine, in each of those pairs, the angles are going to add up to 90 degrees. And again, we're going to come up back to that and explain why that happens. And it actually goes back to something you already know, but probably haven't thought to apply in this situation. So 5 says, draw a picture of a 20, 70, 90 triangle with vertices A, B, and C respectively. Show why the sine of 20 degrees equals the cosine of 70 degrees. So if I draw a triangle here, and it does not have to be to scale. So I have A, B, and C, 20 degrees, 70 degrees, and obviously the right angle is 90 degrees. Now, the reason this works is because the reference angle, the reference angle changes from sine to cosine. So for sine of 20, my reference angle over here is at A. So sine of 20 degrees, I'm looking from angle A. Sine is opposite over hypotenuse. Opposite or across from angle A is side BC. My hypotenuse is represented by AB. So that is the ratio that would get me the sine of 20 degrees. Now they say, well, what about the cosine of 70? Now all of a sudden my reference angle changes to the other side of the triangle, and cosine is adjacent over hypotenuse. Well, adjacent to angle B is side BC, and the hypotenuse is AB. Hopefully you notice that gives them both the same ratio. So BC over AB equals BC over AB. So the sine of 20 degrees equals the cosine of 70 degrees. And again, this comes down to the idea of our reference angle. Remember, sine and cosine, those ratios are based on where are we looking from. When I'm looking for sine, I'm looking from one side of the triangle. Cosine switches to the other angle of the triangle, but they're really both looking at the same part of the triangle, because what is opposite to angle A is adjacent to angle B, and the hypotenuse is going to be the same for the both of them. That AB is not going to change as the hypotenuse. They're both dividing by the same hypotenuse, And really, opposite of angle A and adjacent of angle B is the exact same segment. That is why those two ratios come out to be equal. Six says, draw a picture of a 50, 40, 90 triangle with vertices A, B, and C respectively, and show why the sine of 50 equals the cosine of 40. So again, as we saw in number 5, the sine of 50, so angle A, here is my reference angle when I'm doing the sine of 50 degrees. Opposite of that 50, again, is that BC, and the hypotenuse is AB. Again, I'm looking from angle A, I need the leg opposite it over the hypotenuse. So BC over AB. When I switch to the cosine of 40, that means that now angle B becomes my reference angle for that one. So the cosine of 40 degrees, and cosine now says I want the leg adjacent over the hypotenuse. Well, now that my reference angle has switched over to angle B, again, that becomes BC over AB. And once again, they're both equal to the exact same ratio. BC over AB equals BC over AB. So the sine of 50 degrees equals the cosine of 40 degrees. And again, it comes down to where is your reference angle. Sine is looking from one side of the triangle, cosine is looking from the other side of the triangle in this case. And then question 7 asked us to interpret the following statement. The sine of angle P equals the cosine of 90 minus P, where P is the measure of an acute angle. And this is where I was trying to lead you back in question 4, knowing that question 7 was coming up. All of our combinations in question 4, those angle measures, all added up to 90 degrees. So if I know one of the angle measures, I can subtract it from 90 to find the other acute angle measure. And we're going to show why that works. But the acute angle of a right triangle, or the acute angles, I should say, will always add up to 90 degrees. Making them complementary angles. And this is actually a theorem that the acute angles of a right triangle are complementary. And it goes back to something we know. What do we know about all the angles in any triangle? They add up to 180. So if I use this triangle down here, the measure of angle P plus the measure of angle R plus the measure of angle Q have to equal 180. We said that applies to any triangle. Now, specifically in this triangle, we know the angle Q is 90 degrees. So really the measure of angle P plus the measure of angle R plus 90 equals 180. And if I subtract out that 90 degrees, the measure of angle P plus the measure of angle R equals 90 degrees. So anytime you have a right triangle, you know that the two acute angles have to add up to 90 degrees. Think about it, 45, 45, 30, 60. So now if I look at the measure of angle P plus the measure of angle R equals 90, and I subtract the measure of angle P from both sides, the measure of angle R is 90 minus whatever the measure of angle P is. So that's how that relationship works, is based on what we know about the measures of angles of a triangle.